This is The Chemistry of Plants by Blake and Abby. We're going to go through a virtual lab about the transpiration of plants. Then we're going to go through a PowerPoint that is a little more in depth. In vascular plants, water is absorbed through the roots and carried upward through the stem to the leaves. The force behind this upward movement is called capillary action, a force of attraction between molecules that cause liquids to move up narrow tubes, such as those inside a plant's stem. Some of the water absorbed by the plant's roots is used for photosynthesis, but much is lost to the environment through a process called transpiration. During photosynthesis, tiny pores on the surface of the leaves open to permit the intake of carbon dioxide and the release of oxygen. Because the stomatas must remain open for the exchange of gases, large amounts of water are lost to the environment through evaporation. Water that evaporates from the leaves is continuously replaced with water that is absorbed through the roots. Therefore, a plant's rate of transpiration can be measured by observing the amount of water taken up through a plant's roots over a period of time. The transpiration rate can be approximated by measuring the amount of water taken up in a short time through the plant stem. In laboratory, a plant's transpiration rate can be measured by using a potometer. A potometer can be assembled from standard laboratory materials including a ring stand, clamps, a pipette, a burette, a T-tube, glass tubing, and rubber tubing. To measure transpiration rate, a plant spring is mounted on the potometer and the burette and pipette are filled with water. Over time, the plant will transpire and absorb water through its stems. The potometer is constructed in such a way that the plant's water source is the pipette. Therefore, the amount of water transpired over time can be determined by reading the water level in the pipette. The water supply in the pipette can be replenished from the water supply in the burette by releasing the pinch clamp. In this virtual lab, we're going to find out what factors affect the transpiration rate in plants. We're going to be looking at environmental factors such as heat, light, and wind. We're going to go through 4 plants and compare their transpiration rates. So we're going to start with the rubber plant, and we're going to see its regular transpiration rate, which is 4.9. Then we're going to add the heater, and the temperature increased, which caused the transpiration rate to increase to 6.8. Then we're going to add the fan, which acts as wind, and it caused it to increase even more. Then we're going to add a light, and the light caused it to increase as well. Then we're going to get the zebra plant, and its normal transpiration rate is 4.2. And we're going to add the heater, and then we're going to add the fan, which caused it to increase even more than the heater did. And then we're going to add the light, and then our next plant is the devil's ivy, and we're going to see what its normal transpiration rate is, which is 2.9. Then we're going to add the heater, which causes it to increase to 4.1. Then we'll add the fan, which caused it to increase to 4.6. Then we'll add the lamp, which causes it to increase to 3. Then our last one, which is the arrowhead, and we'll see what its normal transpiration rate is 3.6. Then we'll add the heater, and it increases to 6.6. The fan causes it to increase even more to 7.5. And then the light, which causes it to increase to 4. Then we're going to look at a data table and compare. So for the zebra plant, its normal was 4.2 milliliters, and the fan caused it to increase transpiration rate the most. And the geranium had 1.2 normal, but the heater caused it to increase more than the fan did. And the rubber plant had 4.9 milliliters normally, and the fan caused it to increase to 8.4 milliliters. and the Coleus had 0.9 milliliters normally, and the fan caused it to increase to 6 milliliters. So overall, the fan caused it to increase the most.